So let's begin with the basic thing. What is CFD? What is computational fluid dynamics? The word itself suggests computational fluid dynamics means something, computing some for some variables, computing for some unknown parameters in fluid dynamics. In fluid dynamics means in fluid flow. When a fluid is flowing, there would be some constraint, there will be some variables, and those constants and those variables will result to some they will impact to some system, some outside system or some inner system, and how they govern the system. What is the relationship between those parameters, those variables, and how we can optimize those things, how we can get the maximum benefit, maximum efficiency of any system in which fluid flow is dominated. So those things are to be computed, and computational in the sense for this computing, simple calculator or simple hand calculation won't be enough. We have to use some specialized computer programs. We have to program, we have to do coding for those specific problems, and by the use of computers we will be able to solve. So that's why it's called computational fluid dynamics. Actually this CFD itself, I already told, it's a vast subject. So at this point of time we'll consider CFD as just a numerical tool. It's a tool to solve the fluid flow problems. So now the question arises, why we are interested in fluid flow problems? So why we need to solve the fluid flow problems? Why we want to find the relationship between the parameters of fluid flow? Why it is required? So being an engineer, we are supposed to observe the nature, see the physical phenomena around, get the idea from them, and modify those phenomena, like means utilize those phenomena, utilize natural resources for human benefits at the optimum level. So that is the main goal of engineers. And being a CFD engineers, we will be the keen observer of fluid flow, either natural fluid flow like the flow of wind around the tall structure or tall building, or the flow of river, or like artificially generated fluid flow, like flow inside the IC engine, flow in the compressor, flow from the fan, like those things. So any of those flows will be interested, and the different parameters like pressure, temperature, velocity, density of flow, and the fluid particles, will be interested to find those things, and we'll be interested to find the relationship between these things. And this all is done under CFD. So this is the basic idea of CFD. We can see this feature over here. This is a simple Pelton wheel turbine which is used to generate the hydroelectricity from the conversion of kinetic energy of water into the mechanical energy of turbine. Ultimately we get the electricity by the use of generator. So basic idea here is the overall efficiency of turbine and the output power, it is dependent on the energy of water, and energy of water is dependent on its pressure, its density, its velocity, and its temperature. So how does those parameters govern the efficiency of the system? How does those parameters govern the outcome of this output of this system, and how are they related to each other? So that will be one of the good problem to be solved in CFD. Although this problem can be solved by some analytical method, but this analytical method and this CFD method, they are quite different, and will come soon what is the difference between them and why we prefer CFD over the analytical method, and those things will come soon. So this is one of the example, and next example could be this one, the flight. In flight, generally these are the four main forces acting on the flight: thrust, drag, gravity force, and lift force. So how does the variation of pressure over the surface of wing, pressure over the surface of body, and the velocity variation alongside the body of airplane, and density variation of air, flowing air, how does those variation govern the force like lift, drag, thrust, and gravity. What is the relationship between these things? We can find, we can get the good approximation of those things by the use of CFD. So these are the few examples why we need CFD and why we apply CFD. Uh, so CFD itself is a vast thing, and we can't just describe it in a few words. Along with the time, we'll develop new ideas and new techniques. We'll develop new techniques, and we'll assemble them. We'll keep them together, and time and again, we'll just add up extra things, and our CFD knowledge will go broader and broader. It is endless. Okay, then when generally if someone hears about CFD, this is the picture that comes into mind. This picture basically. यो पिक्चरमा के छ भने एउटा बडी छ, द्याट बडी इज अ कार एन्ड फ्लुइड इज फ्लोइङ ओभर इट. मतलब रिलेटिभ भेलोसिटी छ विन्ड, यो एयरको र कारको रिलेटिभ भेलोसिटी. आइदर विन्ड फ्लो भएर कार स्टेसनरी पनि हुनसक्छ, अर सेम कुरा हो जो जेनरली भइरहेको हुन्छ कि कार मुभ गरेको हुन्छ, विन्ड स्टेसनरी हुन्छ. जसरी पनि रिलेटिभ भेलोसिटी बिट्विन एयर एन्ड बडी. यसले गर्दाखेरि पर्टिकुलर स्पिडमा डिफ्रेन्ट पोइन्ट अफ बडीमा अलग अलग भेलोसिटी हुन्छ. एज आई अलरेडी टोल्ड इन CFD we will be solving for particular parameters, and in this CFD we are interested to know the unknown parameter velocity at each and every point. So these velocities at each and every point, it has been shown in this visualized image. The red color represents the higher velocity and blue represents the lowest. Intermediate we can see from green, yellow and orange color. So this each and every point at each and every time scale, if we are able to find the values for velocity and similarly for pressure and density of air and everything, we will be able to calculate the total frictional loss, total viscous loss to the air by the car. So what is the total loss, and by knowing that we will be able to minimize those losses. Obviously minimizing those losses will be increasing the efficiency of car, increasing the efficiency of engine, and we'll get the better and the best aerodynamicity of this car. So these things can be done by doing CFD. So this is just the final result of the CFD done for the characterization of velocity. This only picture doesn't represent the whole CFD. For this final result, we are supposed to do the calculation for thousands of equations. We have to do a lot of theory. We have to do some coding and everything. And this is the final happy ending of that hard work. So we'll come to this at some point of time. If we do CFD, if we learn and build up new techniques, then we'll reach this point. So now let's think something else. Before even CFD, what is engineering? As an engineer, or as an innovator, or as a scientist, what we are supposed to do? Engineering is nothing but just the utilization of natural resources and use of natural phenomena to optimize them and make them to use for the benefits of human beings. That is engineering. So I'm talking about this thing in this particular CFD. Means there is some relation between this thing. In CFD, we used to study the natural phenomena, and after studying the natural phenomena, we will get some idea, and that natural phenomena will apply. We'll see the results. We'll do computation, and we'll find the relationship between various parameters. And only after studying natural phenomena, we will come to the particular conclusion. So natural phenomena plays important role. So it is valid for not only for CFD but each and every field of engineering, either building a road or making tall buildings or designing a car or making airplane or whatever it may be. Everything is governed by natural phenomena. So we have to study the nature. We have to get the knowledge from the nature and what can be maximized, what can be optimized. So from nature only we can study and we apply it into engineering. So same case is for CFD. So understanding the physical phenomena. As I already told, physical phenomena are the backbone of engineering. Without understanding physical phenomena, no one can do just sitting on the lab and inventing something. It's